answer in the at about 95. That's the so-called second string revolution. So the main upshot achievement for the second string revolution, trying to address this question, the main conclusion is that string theory turns out is not just a theory of strings. So this sounds very, maybe, well, when I look at it, I think it's okay. There's nothing wrong with it. But the first time you look at it, maybe it's a bit strange the way to say this. So because we start from the theory of strings, and now we say string theory is not just a theory of strings. So what is going on? So let me now move to the second part of this colloquium. So in the second string revolution, I can say that many of the development in the second string revolution are related to understanding about a new property of geometry and symmetry in string theory. So one of the first things people understood is about duality symmetry in M theory, in string and M theory. So what do I mean by duality? Many of you have experience in condensed matter physics. At least undergraduate level, you have learned condensed matter physics. So maybe you have seen a model called Ising model. It's a two-dimensional lattice model with charge, with spin interacting with labor next to labor, interacting with labor, right? It's a simple model of spin. It turns out that model actually you can solve it exactly, and also that model has an interesting property, which is the model at low temperature actually is due to the same model at high temperature. So there's a low temperature, high temperature duality. That means you observe a system of this Ising model at some temperature. You cannot really tell if the temperature is T or 1 over T. There's a duality there, right? That's a kind of duality. The other duality, which you may be familiar, if you are doing quantum field theory, there's a duality in 2 dimensions which relate boson and fermion. That's a bosonization map. Or if you actually, there's something even more fundamental in Maxwell theory. You have a duality between electric field and magnetic field. You look at the Maxwell equation. If you change E to B and B to minus E, you leave the system invariant. So that's another duality. So duality is not unfamiliar. So here I'm just talking about another example of duality. But this duality is realized in string theory. So since the middle of the 90s, people have started to call it evidence. I cannot tell you the evidence, but people find evidence that this 5-string theory, which I wrote down before, type 1, type 2, and the hyperbolic one, people used to think they are different theory, but in fact they are the same. So this is very strange thing. I cannot explain to you in detail how strange it is, but basically some of this string theory, for example, I said before, they have a gauge group with they have a non-abelian gauge group, and then some of the other theory, they don't really have a non-abelian gauge group, but still there could be a duality between them. They could still describe the same theory. So what you think about as gauge boson in one theory actually become something not describing just matter, for example, not gauge boson in another theory. So to prove it, of course, to prove this duality, of course, is not so simple, and in fact, has remained as a conjecture. Nobody is able to prove it. But technically, you can imagine it's something just like doing Ising model. Ising model, you can solve it exactly, so that's why you can establish the duality exactly. But this model is this string theory, of course, is much more complicated. But it's difficult to establish the statement precisely. But still, there's a lot of evidence you can check, and then it's all point to the same consistent picture. So the picture now is that these 5 theories are connected to each other by duality transformation. So this is the picture. So in this picture here, this is like the space of all theory. So before we thought we have 5 theory, right? But in fact, there are not 5 theory. There are just 5 theory, 5 different limits of one theory, which is called M theory, and there are just different limits of this theory. In that limit, then the theory, the unified underlying theory, which is called M theory, behaves like a heterotic O type or a type 2A type or different type. Right? So the picture now which emerges is that there's a fundamental theory which is called M theory, and which encompass all the 5-string theory in 10 dimension. This is a conjecture by Witten in 1995. So in 1995, Witten proposed the existence of, and argued the existence of this theory called M theory, and perform and he performed many checks, and other people have also performed many checks afterward. And so for this existence of this theory, as a conjecture, people didn't actually Witten didn't give you any construction about this theory. So for example, what's the dynamical equation? And when you say you have a theory, of course you want equation you can work with, you can solve, and then you can use it to tell some physical explain some physics. But actually, Witten didn't give you a workable definition of M theory. Now, to establish this duality, rely on something which is very important, which is called D-branes. So this refers back to my statement earlier that string theory is not just a theory of strings. So what happens is that so in a very simple way to explain it, you can D-branes are just a high-dimensional object, like a solitonic object in the string theory. So for those of you who are more familiar with gauge theory, you can have solitonic object in the point particle theory. You start from a point particle theory for SU2, for example. You can have a domain wall, right? And you have vortex strings, and you can also have a monopole. Or monopole is just like particle, but vortex string and domain wall, these are high-dimensional extended objects in the theory. So D-branes are very much like that. At least in the beginning, you can think about it like that. So you can think about D-brane as a soliton, as a composite, not fundamental, composite object in the theory of strings. In fact, this is how people discovered it in the beginning, using low energy theory of strings. But what is important for this duality to work is that the D-brane actually look like it's a soliton in one theory, but it actually is a fundamental object in the other theory. So the D-branes actually, depending on which theory you look at, it can be a fundamental object too. So that's a picture which got established in this second revolution. So now I say a little bit more about what D-brane is. A D-brane is an extended object. Usually we give a label here called P. So a DP brane is a brane with a p-dimensional space at one time. There's always a time, and it's an object. It's like a hyperplane, like a blackboard here, for example. The blackboard here is a 2-dimensional space and with one time. So the blackboard I can call it a D2 brane, right? It's a brane where open string can end. This is a defining statement for a D brane. So all the physical properties of a D brane can be worked out from looking at the physics of open string. So the open string, which end on the D brane, basically define the physics of D brane for you. Now the picture is very. I think you can get a similar picture in the following example. For example, you probably have seen a tornado, right? In US, in Florida, for example, recently there's some tornado, big storm. You can see the storm and then go big cloud and then eventually come to the ground, connect to the ground. So this is a tornado. You can think about this. The tornado is like the open string, and the ground is like the D ring for you. Now, but one fundamental difference of this picture and the string is that in the case of tornado, the tornado doesn't. It's not a definition of the physics of what happened on the ground. Right? It's just a phenomenon in which you have two objects there. They got connected on the ground due to some geo and climate physics of climate. But in the case of string theory, this is rather different. The tornado here, the open string, is defining what the physics of D brane for you. In fact, the D brane wouldn't have a life itself if you take out all the open string. So that's the D brane, because the D brane is defined by the open string, and the open string can vibrate, right? So the D brane is a dynamical object, and there's a theory as a theory on the D-ring. So for example, if you think about a particular example where P is equal to 3, so this is an object with 3-dimensional space and 1 time, so it's called D-free brane. So on the D-free brane, you have this kind of particle spectrum. You have a gauge field and then a number of scalar. But the details is not important, but you have a 4-dimensional gauge field and a number of scalar and number of fermion. The main thing I want to say is that there's no gravity on this brane. You don't have graviton, basically because it's coming from an open string. You don't have open string doesn't give you graviton. Closed string gives you graviton. Open string doesn't give you graviton. So this is actually very interesting to have a D brane whose well volume theory is a gauge theory. So of course we know the standard model is based on gauge theory, and for a long time people in string theory have been trying, or people working in string phenomenology has been trying to construct a standard model from compactification, basically from closed string physics. So but you met with the problem of vacuum and the uniqueness of vacuum and choice of the Calabi-Yau manifold. That is unsolved. But so in the modern age, after the discovery of D brane, people have tried to work in a different way. So try to obtain the standard model other than from the closed string, but now from open string. So you have this kind of construction. You can have a D brane. So you say the world is not because of compactification. The world is 4-dimensional, not because of compactification. The world is 4-dimensional just because we are living on a tortoise. This tortoise is a D brane. It is a D-free brane. So we are living on the tortoise. This tortoise has a theory, which is just a gauge theory. So this is our standard model. So of course, this is a simple example. This doesn't look like a standard model itself, but you can have arranged more complicated configuration of the D brane, and then in principle you can. There's no problem to construct something look like the standard model of the world, right? But then of course the question remains: why this particular set of D brane? Why not another set of D brane? We should consider. So there's still the same question about uniqueness of a string solution. But this is a different way of thinking about phenomenology, and has been the way in the last 10 years or so for people working on string phenomenology. So this is a case when you have one D brane. So of course you can have many D brane, and they overlap, right? So just like you open a book, you have one page of the book, but you can have a whole book with all the pages stick together. So that's so-called overlapping, right? So you can have overlapping set of branes. In that case, something interesting. On each brane you have a U1 gauge field. When you have n of them, you have n of this U1 gauge field. So you will say, okay, the gauge symmetry is just U1 to the power n. But in fact it's wrong. So again due to Witten, it shows that the symmetry is enhanced to a non-abelian gauge symmetry. So when you put brane together, the U1 or the abelian gauge symmetry got enhanced to non-abelian gauge symmetry. So in other words, if you want to do phenomenology of standard model, you have to consider overlapping branes, because we know the gauge group are non-abelian. So that's one thing I think is quite interesting. This is
What do you mean?
Yeah. Sorry.
What do you mean enhance?
Enhance, yeah. So enhance mean without this mechanism, the rank of the gauge group is just n. U1, or the gauge group is just U1 to the n. If you count the generator, it's just n generator. But then if the symmetry is enhanced, in this case to Un, the generator is n squared. So you have a lot more boson, gauge boson. So instead of having n U1 gauge boson, you have n squared, you have W and Z. So enhancement in this sense. Thank you. So now, apart from this interesting phenomena of enhancement of symmetry in D brane, this D brane also allows you to give a definition of what M theory is. So what Witten didn't achieve in his paper. So this is quite a technical thing here. So the only thing I want you to get away from this is that these 4 people, Banks, Fischler, Schenker, and Susskind, these 4 people was able to use some simple, I think quite simple, and argument, and also convincing argument to show that the M theory we can talk about can be captured by the physics of a large number of these zero rings. So n is supposed to be very large. So instead of a 11-dimensional theory, these people after a series of arguments show that you can capture the 11-dimensional physics by looking at quantum mechanics, because these zero are particles, right? So zero means there's no space, so it's just particles. So a large number of particles, basically a gas of particle. From that gas of particle, you look at the quantum mechanics, which has this particular form. So quantum mechanics has a kinetic term. So these x are the position of the d0 ring. So it's a quantum mechanics of the position of the d0 ring with the kinetic term, and then you have a potential term. So this is just a ke minus the pe, right? The pe is based on the commutator of the position of the d0 ring square. So it's a particular form and then some fermion because it's a supersymmetric quantum mechanics. So the whole conjecture of M theory due to BFSS is that all the dynamical aspect, quantum aspect of M theory are captured by this very simple one-line action. So if this conjecture is correct, then we are supposed to have the final solution for the theory of everything, because we don't need 5-string theory, because all the 5-string theory are supposed to be different limit of this M theory, and then now this is the supposed to be defining definition of M theory. So this would be too good to be true. What I mean is that this is a conjecture, and so far there's nothing which people find wrong with this conjecture. But the main problem is that even if this conjecture is correct, we are still far away from be able to use it in practice, in practical sense. Because the way the conjecture works is that although we say the dynamics of the M theory are all encoded in terms of this action, but what is missing is that the dictionary, how to encode the physics of the 11th dimension in terms of a quantum mechanical process of the D0 ring, that part is actually missing. So all you can say is that it's contained there. But how do you work out or how to extract information from the quantum mechanics to actually do something about M theory? That part is unknown. So if that is unknown, then I think, of course, it's better than nothing, but it's still, I think objectively, I would say that although it's better than nothing, it's still not very useful to have this definition. But I will give you the application later of this action, which actually is very, I think, is very interesting. Another new development associated with D-brain is this non-complete geometry. So this is something that Pei-Ming and I worked out. I think it's the first. I don't remember now. But it's one of the first papers we worked out together after we graduated from Berkeley. Yeah. So at that time, D-brain got very first in '95 we got discovered D-brain by Bosinski, and then people start using D-brain in all kind of phenomena. What we find is that if you put on a background field on the world volume of the D-brain, then the D-brain become the geometry. So these x are the coordinate of the D-brain. They don't have a vanishing commutator, so they become non-vanishing. So this is called a non-commutative geometry. Basically, the geometry of in an ordinary geometry are described by function, and the function commutes. So x times y is equal to y times x, or 3 times 5 is equal to 5 times 3. This is something we know all our lives since as a kid. But now what happens is that if you have a background field, this background field is one of those fields in string theory. It's a field which has 2 indices. So this generalize the abelian gauge field of U1, so of a Maxwell field. Then the geometry becomes quantized because this relation cannot be represented as a function. It can be realized only if x become operator. So this is quantized. So you can prove this by looking at this picture here, but I don't think you can see it yet. It's basically by, again, looking at how open string ending on a D-brain. So the same picture. So I say D-brain are defined by open string. So again, you can now put a B background field and then derive this relation. Now this is quite interesting. This relation itself. we don't propose this relation, but we give a proof for this relation. But this relation is quite interesting by itself, even without string theory, because first of all, theta can be non-zero, but it can also be very small. So when we talk about very small, that means in principle we can test it. In principle, it can be possible that in the world is actually non-commutative, but then it's so small, so in ordinary experience we don't actually see it. But if you go to some experiment, maybe you can design an experiment to look for it. So in fact, people have done it, but of course, so far it's consistent with theta being 0. Right? But it's an interesting possibility for phenomenology. Once you have that, then it's a natural question to ask whether you have some other new form of quantum geometry. Why are we interested in quantum geometry? One reason is that we believe in the early universe, like near the Big Bang singularity, where quantum mechanical effects are supposed to be very strong because the energy is infinite, right, at the Big Bang, and the temperature is infinite. So you expect quantum mechanical effect to be very strong. So you have to study quantum cosmology. You have to study cosmology, not just using Einstein gravity. You have to use quantum mechanics together. But when you try to combine the two things together, you find that there's a limit on the extent you can apply general relativity. Basically, around Planck scale, and you find that the Einstein equation should break down, and probably it will be replaced by something fundamental in quantum mechanics, which is non-commutativity, right? So there's a belief among theorists. I think even Heisenberg already made this proposal that but of course Heisenberg is the reason for him to look at non-commutativity is different. He wants to resolve the UV divergences of quantum field theory, but there's a reason to study this kind of non-commutative geometry. So in string theory, then it's interesting to ask whether you have other form of non-commutative geometry other than the one I wrote down before. Then in a recent development with my student, we found that it's possible to have this kind of generalization of the previous relation. So this defines a new form of non-commutative geometry. The x here are supposed to be operator, and this bracket with 3 slots are defined by this relation here. So this is just a generalization of the commutator. If you have f and g, then you have only 2 ways to put f and g, fg or gf, and then for the different order you put a minus sign. If you have f, g, and h, there are 6 ways you can order f, g, h, right? And then some of them you put a plus, the other one you put a minus. Basically, depend on the commutation. So this is called the alternator of f, g, h. Now this geometry is defined by this alternator not equal to 0. How you derive it? There's some statement here, but I don't think we care about that. So basically, M theory, there's some similar setup of D-brane in B field stuff, and you can derive it. And the theta is again related to some background field in the problem. Now, what is interesting is that this bracket actually was something Lambu discussed already in 73 for different reasons. So Lambu in 73, he tried to ask the question whether quantum mechanics could be generalized in a more general form, but keeping the fundamental property of a new field. So you want probability to be conserved. So he for that effort, he introduced a new form of mechanics, which is called Lambu mechanics, which is based on some free bracket called Lambu bracket. It's a generalization of Poisson bracket. And then if you quantize that mechanics, then you presumably get a generalization of the quantum mechanics, which is based on a Lambu bracket. So that's called quantum Lambu bracket. And this is one of the possibilities Lambu considered. So it's natural for us to call this a quantum Lambu geometry. Similar to the previous geometry, then it's an interesting question to ask whether this is realized in nature. So one can try to build a quantum field theory for example, standard model based on this kind of deformation and try to look for a signal or constraint how large is theta. But that part is not done. But for those of you graduate students here, I think that could be an interesting project. Now, I come to the third point about generation of space-time. Now, A very perhaps fundamental and perhaps even crazy question is to ask what exactly is space-time? We are so used to space-time. All the physics we talk about are based on function on space-time, right? So we are so used to field theory or whatever. Everything space-time is like a platform for everything else to happen. So we usually keep that in a different place. But now people start asking, at least in string theory, we start asking whether what exactly is space-time, and why is space-time 4-dimensional? Why is there time to start with? Or is it possible that space-time itself is not something fundamental, but like an emergent property or a derived concept? Why do we ask this kind of question? Actually, it's not just string theories. I think for a long time people start asking this. I think probably the first time people start asking this kind of question was because of general relativity. In general relativity, space-time, of course, is not absolute anymore. It's dynamical. It can be altered by energy momentum tensor of matter. So space-time somehow become dynamical. Then perhaps it's actually it's not just a fact. It actually could be emergent or derived by something more fundamental. Right? That's a possibility. 4-dimension. I think again because of Einstein. Einstein tells you don't look at x, y, z, and t. You introduce a notation x mu to keep notation simple. And once you have this notation, nothing stops you to change mu from 0, 1, 2, 3 to 0 to d. So it's just a simple generalization, and people like simple generalization. So of course, then space-time can be any dimension, and in any because of this vector notation, we can write down physics in arbitrary dimension easily, right? So then you can ask the question, why then is space-time 4-dimensional, or why the physics prefer 4-dimension? Why is the world is 4-dimensional? So this kind of question people like to ask, but of course so far we don't have a framework to actually address this question because we use space-time as a fundamental starting point already. So once you fix your first starting point, you write down a theory of 4-dimension. You don't have any freedom to actually ask why is 4-dimension instead of 5-dimension, right? But now I tell you the different perspective from string theory. In string theory, it's possible to address this question. So I think this is quite interesting. Remember I said M theory, right? There's a 11-dimensional M theory. Everything is supposed to be determined by the quantum mechanics of this D0 particle. So if I look back at this theory of Bang, Fisher, Schenker, and Susskind, the equation of motion are just like that. So it's just F to ma. So this acceleration, right, equal to some force, and this force is coming from the potential I have before, and then you differentiate dv dx. So this is basically that equation of motion. Now suppose we look at a static solution. So we don't have any acceleration. So we just want to have a solution satisfying this equation. Then one of the possible solutions, I mean there are many other solutions, but one of the possible solutions is that you just have a constant commutator. So x is equal to I theta 1, and theta is a constant. And the commutator, when you substitute the 1 here, of course is 0. Right? So this is a possible solution. Now this solution is interesting because you may remember this is a solution for a non-commutative geometry. So for example, I can have a solution for theta, which is theta 1 to 0. And this solution corresponds to a 2-dimensional non-commutative space. Okay, of course, then what else? What next? It sounds interesting to generate some mathematical solution from string theory, but it doesn't mean anything because we are talking about real physical world, right? So, in fact, you can do something more, right? You have an object here, this solution here. If you want to really see what this solution means, then what you can do, right? So we are physicists, or at least most of us are physicists, and probably all of us are physicists. The way we test things is that you hit it. If you don't know whether someone is happy or you hit it, you probably tell I'm not happy. If you don't know what this is, you hit it. So give something, it could be a push, and then you get a response. That's how you do experiment. And now we can do experiment theoretically. So we can try to disturb the solution and try to see what's the response, and then from there we can see what this actually corresponds to. So let me change the notation a little bit. The solution I use now small x to represent the solution.